So we're going to do another example here. We're going to show that the function has exactly 1, 0 on the given interval, one solution. And in order to do this, we have to show two things. We have to show that there exists a solution, and we do that using the intermediate value theorem. And then we also want to show that the derivative is either always positive or always negative. Because remember now, the derivative starts telling us about the shape of the graph, and if the derivative is positive, we know that the graph is increasing, and if it's negative, we know the graph is decreasing. So if the graph is always increasing or always decreasing, then there's only one opportunity for that function to cross the x-axis. Because if it changed from increasing to decreasing, then there might be two spots where we could cross the x-axis. All right, so I'm going to do my intermediate value theorem first. And when I do the intermediate value theorem, I just need to pick two values to plug in. And this could be a little bit of trial and error. But I can evaluate r at theta equals, we'll say theta equals 0. So r of theta, if I plug 0 into all of these, I get out -8. Similarly, I could let theta equal 8. So r of 8, if I were to plug 8 in, I would end up with sine squared of 8/3. And sine squared of 8/3 is approximately 0.002. Okay? And that would be in radians. But what we notice is we have a negative value and a positive value. So there's one point that's below the x-axis and there's one point above. And this allows us to say there's at least one solution. But at least is different than exactly. So for exactly, we also want to show that that derivative is always going to be positive or always going to be negative. So I'm going to give myself a little bit of space here. I'm going to rewrite my function. R of theta is theta plus sine of theta over 3 quantity squared minus 8. So my derivative, r prime of theta, derivative of theta is 1. When I go to take the derivative of sine squared theta over 3, I have to use the chain rule twice. I'm going to get 2 sine of theta over 3 times the derivative of the inside. Derivative of sine, I've got cosine of theta over 3 times the derivative of the inside there, which is just going to be 1/3. And then the derivative of that 8 value would be 0. So what I have here for my derivative, I'll just clean my notation up a little bit. R prime of theta equals 1 plus 2/3 sine theta over 3 cosine theta over 3. And because we always like to refresh our mind and use our identities, this identity right here that we're looking at is the same as sine of 2 theta. So it's a double angle identity. So I can say r prime of theta is 1 plus 1/3. And the double angle, that's going to be sine of 2 theta over 3. All right, and if we graph this, if we think about our graph, we get a sine curve that is always above the x-axis. And so what we can say is that r prime of theta, every output I'm ever going to get for this function is always going to be positive. So if the derivative is always positive, right, this derivative here is always positive, then the function is always increasing. So what we've said is we have a function that's constantly increasing. It's always rising from left to right, and it has at least one solution. Well, if it's always rising, there's only one possible spot it could cross the x-axis. It's never going to turn back around and become decreasing. So thinking about what we were asked to do, we wanted to show that there was exactly one solution, and we showed two things. We showed that the graph was always increasing because the derivative is always positive, and then we also showed that by the intermediate value theorem there's at least one solution. So we have another problem we're going to work on here. For what values of a, m, and b does this piecewise function satisfy the hypothesis of the mean value theorem on the interval, the closed interval from 0 to 2. Okay, so basically we need to determine what A, B, and M are. And so we have to think about, well, what does the mean value theorem say? Right? It says that it has to be a smooth, differentiable, continuous function. If it's not smooth, it's not differentiable. So let's think about what we're looking at. We have our constraints here, and our constraints are just letting me know that I'm moving from 0 to 2, right? We're dealing with these x values on the closed interval. So we know it's a closed interval, and we need to show that it is smooth, differentiable, and then also continuous. So since f of x must be continuous, and it needs to be a smooth, continuous curve at x equals 0 and at x equals 1, because that's where we have some changes occurring in here, right? At 0 and at 1. So let's think about what this graph looks like. So the top piece of our piecewise function says y equals 3 at x equals 0. So what that gives me is right here, y equals 3 at x equals 0. I have a solid dot. And then my next piece is a parabola, right? It's a parabola with a negative leading coefficient, so that lets me know it's some sort of parabola opening down. So we've got some sort of curve going on there. We can't touch there, but we also cannot touch at this end. Okay, so we've got this parabola with these open circles. But of course, the 3 on the x-axis plugs up that open circle on the the left bound of the parabola. And then our bottom piece is linear. So we need to figure out, and it's going to be occurring between 1 and 2. We need to figure out how to make this line. So we've got a parabola occurring from 0 to 1, and then a line occurring from 1 to 2. And essentially, we want that curve and line to be very smooth. Okay, so we need to make that continuous. And what I'm going to do is I'm going to think about left-hand and right-hand limits. So the limit as x approaches 0 from the right of my function f, as x approaches 0 from the right, we're going to get that output value, the y-intercept, right? The y-intercept of this parabola is going to be a. So f of 0 is a, which is the y-intercept. And if we look at the limit as x approaches 0 from the left of f of x, that would equal 3, because from the left, we would just be going towards that ordered pair, 3, 0, 3. So what we can determine here is that that A value must equal 3. So, because we know that the A, I'm going to plug my 3 in up there, we can think about the limit as we approach 1 from the left and the right. And what we know is that they need to meet. So the limit as x approaches positive 1 from the left of my function needs to equal the limit as x approaches 1 from the right of my function, because we want them to meet at the exact same point. So what I'm going to do is I'm going to consider f of x at x equals 1. And so f of 1, we have that parabola, -1 squared plus 3 times 1 plus a. And of course, we just said that that a value is going to be 3. So if I plug these in and I simplify this, what I get for my output is that f of 1 equals 5. So what's occurring is we now know this point right here is 1, 5. So I need to make my line so that it touches right at that point. And so since f of 1 equals 5, then we know 5 needs to equal mx plus b. And if I'm to plug in 1 for x, because I'm considering this at x equals 1, I can say that 5 equals m plus b. So since, I'll write in this color, since f of x must be differentiable at that point, 1, 5, now that we know this, we can say the limit as x approaches 1 from the left, so on our curve, f prime of x of the derivative needs to equal the limit as x approaches 1 from the right of the derivative. And basically we're saying that they both need to have the same slope. So approaching from the left, we have that quadratic formula. F of x from the left is, we've got negative x squared plus 3x plus 3, so that's my f. So f prime is negative 2x plus 3. And we need to evaluate f prime at x equals 1. And so we do the same thing with the line. If we consider that line f equals mx plus b, and we were taking the derivative of that, we would get that f prime equals m. And if we evaluate that at x equals 1, so plugging 1 into the derivative as we approach that function from the left is going to give us a slope of negative 2x plus 3. If I plug in 1, I get 1, and that needs to equal, if I plug x equals 1 into m, it doesn't change anything, I get m. So now I know that my m value equals 1. And so if I know that, as we wrote up above, 5 equals m plus b, 5 equals 1 plus b, subtract the 1, we'll get 4 equals b. So my piecewise function that I started with, so it was 3 at x equals 0, my quadratic piece, negative x squared plus 3x plus 3, and that occurs for an x value between 0 and 1. And then my line would be 1x plus 4, and that is occurring when x is between 1 and 2. Okay? So just to recap, my a value would need to be 3, my m value would need to be 1, and my b value would equal 4. So we have one last problem here, talking about temperature change. And we're going to say it took 14 seconds for a mercury thermometer to rise from negative 19 degrees Celsius to 100 degrees Celsius when it was taken from a freezer and placed in boiling water. Show that somewhere along the way, the mercury was rising at a rate of 8.5 degrees Celsius per second. And so we can do this very easily if we use the mean value theorem. Because if we can show that there's a slope between t equals 0 and t equals 14 that's equal to 8.5 positive value, then we know that somewhere between 0 and 14 that slope of the tangent line would have also existed. So in this case we'll say t equals 0, and that gives us a degree in Celsius of negative 19 degrees. And t equals 14 gives us a Celsius degrees of positive 100. So thinking about that as ordered pairs and using time as my x value, I have 0, negative 19, and 14, 100. So if I go and I find the slope of the secant line, that's just my regular slope formula, 100 minus negative 19 over 14 minus 0, I get negative 119 over 14, which is 8.5, and that is degrees Celsius per second. And so we can say then, since the secant line has a slope of 8.5 Celsius per second, then by our mean value theorem we learned about, there is a tangent slope of 8.5 somewhere on that interval from 0 to 14.